Hi everyone, this video is going to be the first video of the playlist where we are going to discuss in detail about PyTorch framework. So first let's try to understand what the PyTorch framework is. So PyTorch is actually an open source machine learning framework much like sklearn and TensorFlow, which are the other two machine learning frameworks available in the market. Um, it provides a wide range of tools and functionalities for building and training neural networks. When we talk about a neural network, it could be either a shallow network, which is a network with just one layer, or it can be a deep neural network, which will consist of many hidden layers. So it was developed by Facebook's AI Research Lab and released in 2016. And as we are recording this video, the version 2.0 of PyTorch is available in the market. So PyTorch is very much known for its dynamic computational graph. It's a concept which we have already discussed in detail in the ANN playlist, and I will link up the suitable video describing the same, and I will urge you to revisit the video before following this video to make understanding clear. And in any case, when we are understanding the problem statement, I will walk you through the concept of computational graph as well. So one of the other advantage of PyTorch is the usage of tensor. So before proceeding further, it's very important for us to understand what a tensor ideally means. A tensor is a mathematical object that represents the multidimensional array of numerical values. We may need tensors in our day-to-day data structure algorithms, but over there we use it with a different name called as an array. So both tensors and array have overlapping characteristics, but tensors have a more formal mathematical foundation and they have greater flexibility in the terms of rank. For example, a scalar is a rank 0 tensor, a 2D array is a rank 1 tensor, and so on. The tensors have specific mathematical operations defined on them, and hence they are used in the training of the neural networks. We will definitely use tensors over here, and whenever we are going to progress to the coding part, we will try to understand how to handle the tensors and its data types in much detail. So let's walk you through the problem statement we will be solving today and how we can correlate the problem statement with the theory which we have already learned in the previous videos. So I open something called as a collab over here. So I load few of the libraries which we will be needing, which is NumPy, Pandas, and Matplotlib. All of them are pretty basic EDA libraries. I already have a data set prepared. And if we just see the sample of 5 observations from it, it is consisting of X and Y. The entire objective is to take into account the value of X and try to approximate it with a functional value y. Now let's see how the scatter plot corresponding to the data which we have looks like. So this is the scatter plot which we are having, and by the look of it, it looks much like an exponential function. So what we can say is if we have x as the domain and y as the range, then we can find a function f which is of form e raised to wx plus b, and we have to estimate the parameters w and b using suitable methods, because the trend which we are seeing over here for different values of y corresponding to distinct values of x is ideally an exponential trend. Now what we do, we save the values of x and y over here, in the form of numpy arrays, and try to understand the problem from mathematical point of view first before delving deep into the tensors and the PyTorch framework overall. So from my understanding of the data, we can say that we have y hat, which could be represented in the form of e raised to wx plus b. Over here, w and b both are unknowns. And this is exactly how the curve is exactly looking like. This is the curve which we saw in the code. And what we see is it's some sort of an exponential function. We approximate it as this y hat raised to wx plus b. The only drawback which we know is we don't know the exact value corresponding to w and b. While we definitely know what x is actually a unidimensional vector which is represented over here, and from the data we can clearly see x is taking value between 0 and 1. So we know what our x are. We don't know what the values or the parameters w and b are possibly. So we will use the principle of least square, where we consider a loss and we try to say that we need to minimize the deviation between y and y hat, and we use the squared error deviation. Now we expand it further, or we substitute the value of y hat, then we get e raised to wx plus b whole square. So this is the loss function we are getting. And if we have to apply the principle of least square, we have to differentiate it with both w and b and equate it to 0 and keep on, or if I have to apply a stochastic gradient descent on top of it, we have to calculate the gradients and keep on updating the parameters once for all, and the process will go on till a finite number of steps where the loss is very minimal. So we have to minimize the loss and at the same time find the values of W and B. Now let's try to understand what this computational graph means. And this is going to be a review of how the computational graphs are calculated in Torch in the first place. And that's a basic understanding. So this entire equation which we are having over here, we are going to represent it in the form of nodes and graph. So we see the first operation being done is Wx. We write W over here, we write x over here, and then we try to mention the operation which we are performing, which is multiplication. Yeah. Now we have another node which is b, and what we are observing is after multiplying w with x, there is an operation of addition which is involved over here. We mentioned it. We proceed further with calculating the exp. Yeah, so this completes this entire expression. What we observe is this exponential is multiplied with -1. So we do that as well. So this becomes another node. Now what we see, we are adding y to it as well. So we put a term as y over here. We proceed further, even further, and then we perform an operation of addition to it. Now the entire term within the bracket is resolved. The next step which we can do is square it. So we mention that operation as well. Now, so we see that if we move from left to right, the entire expression of loss is ideally represented in the form of a computational graph over here. So let's try to recall our concepts a bit, and let's name these nodes as sub-values. I name it as A, B, C, and D over here. I name it as E over here. I name it as F. Then this could be G, this is H, this is I, and eventually J. Now, the first thing which we need to compute over here is grad L by grad W, or del L by del W, which is nothing but del J by, and we have to look up where exactly W lies. It's corresponding to A. So we have to find del J by del A. The process to calculate this is pretty simple. As mentioned in the video, which I will be providing in the description link, you can find a path from J to A, which will be like J, I. So we have to propagate backward. So J, I, then we can say that it is H, then this is G, this is F, this is E, and eventually this is A. The first thing we do is we put a del symbol over here. We do that, and then we copy the successive term in the denominator. So this becomes del I, this becomes del H, this becomes del G, this becomes del F, this becomes del E, and this becomes del A, and del A becomes del W. Now this becomes the entire chain rule for your differentiation. So we can decompose del L by del W into a chain rule of this sort. Now we always used to create a table for this task. Let's do that as well. So over here, over here we have A, which is represented as W. We have B, which is represented as X. We have C, which is represented as B. We have D, which is represented as Y. Now we have to write E as well, which is represented by AB. So if I scroll it a bit up, so E is the multiplication of W and X. W and X are formally defined as A and B. So we can write E as AB as well. Now we proceed further. We write F, or let me make this graph visible to you so that you can correlate better. So we can write F. So this is complete. So we can write F, which is equal to E plus D. We can write G, which is equal to E raised to F, if I'm not wrong, yes. And H is minus G, and I is H plus D, and eventually J is I square. Now, if I just try to do the differentiation over here, del J by del I will give you 2 twice of I, del I by del H will give you just 1, del H, we have to just focus over here, like this J and I square, the relationship is here. So if I do the differentiation, I'm just going to get twice of I over here. Now, if I is already there, as you can see over here, so if I do the differentiation with respect to h, we are just going to get 1. We go to h, we try to differentiate with respect to g, we are getting minus 1. We have g, we differentiate, so this is g and f which we are having. We differentiate with respect to f, we are getting e raised to f. And for f, we are getting e, so with respect to e, we are getting 1. E and e, so this is b, so E is equivalent to AB over here. Now if I differentiate with respect to it, only B term will be left. And eventually we are going to get 1. So now the overall term comes out to be twice of I B e raised to f with a negative sign. So this is how a gradient is calculated, and this is the gradient of loss function with respect to W. Now I can substitute back the term and get the value. So here f is going to be e plus c, e is your wx plus c. So we are getting wx plus b over here, and g is going to be e raised to wx plus b, and we just take the negative over here, e raised to wx plus b is written over here as well, and I is going to be h plus t. This is h already and d is y. So y minus e raised to wx plus b. Now if I have to expand this term clearly, I just have to substitute the values which I am getting over here. So on substituting, we will get something which will be similar to this. So the negative sign will remain as it is, twice will be there. I take the value of I, which is y minus e raised to wx plus b. This is understandable. B is equivalent to x, and e raised to f. E raised to f is something which is over here. So it will be equal to e raised to wx plus b. So this is the gradient of loss with respect to w I am getting. Now if I recall how a stochastic gradient descent works, so it is ideally of this form that we have a term at t plus 1, which is equal to wt minus eta of del L by del WT. Now we have already found out the expression of del L by del WT over here. We can plug it, and WT we can start with an initial value W naught and keep on propagating with respect to an input parameter eta, and then try to understand how we have to impose a stopping criteria so that wt plus 1 is initial, or wt plus 1 is finalized at one step. So this is with respect to W. Now we can do a similar step with respect to B as well. Now there is one thing which we are seeing over here. Even with a small function like this, where only a univariate feature is there, we are getting some really complex calculations to do. So The task of simplifying these complex calculations is done quite nicely by PyTorch framework. We can ideally do the entire steps as we have elaborated over here on pen and paper, but if we are using a PyTorch framework, everything is done inherently into it. It's because of the fact that it supports something called as automatic differentiation. The entire thing which we did over here, finding the path as well as the chain rule, it's done in PyTorch as AutoGrad. It allows you to compute the gradients automatically for any differentiable function defined using PyTorch tensors. So this is an important concept that for enabling the AutoGrad, we have to use PyTorch tensors, something which when we are going to code right now in few minutes, we will be explaining in detail how to initialize the tensors and use it. But the AutoGrad will make it very much simple for us to not build the graph from the scratch and do it, which we would have otherwise done if we had been in frameworks like NumPy. We would have actually calculated the entire graph, or we would have calculated the gradients, and we would try to do the calculations numerically, which is not that efficient way to do. But PyTorch enables us to do all the calculations in the backend, or the graph computation which is being created over here, which we are manually doing in the backend, making the calculations much easy for us to follow. So this was for the computational graph understanding. Now let's jump to the code and see how we are going to actually do it. So the first and foremost thing which we are going to do is to convert the numpy values of x and y in the form of torch tensors. Because we have just defined that in order to enable the AutoGrad, we should be having the torch tensors at place. That using torch dot from underscore numpy, we write it as x, and just like we have reshape in numpy, we use view over here, and similarly we follow the same thing for y as well. Yep. And then we try to see the shape. Yeah, so over here what we can see is we are having two tensors, torch tensors of size 227 cross 1. So we just did one thing. We took the columns x and y and we reshaped it in the form of torch tensors. That's it. Now we will proceed further with creating our own custom model, which will be looking somewhat like this. This is our custom shallow network which we are building. We just discussed in the text that this is how our function is going to look like. So this is how the function is supposed to be looking like. So we are going to build our network according to this only. So for that we specify a class which we are going to use, and this is having a parent class as well. So just to understand what we are doing over here, we are calling a very generic class of Python, which is the base class for all neural network modules. And that is called nn.module. You may have seen that when we were loading the import step, we did load import torch.nn as nn. So this is the base class for all the neural network modules, and whenever we are building a custom model, because we are going to use AutoGrad on top of it, and we have to deal with torch tensors as well, it's always advisable to call this as the parent class for any class we build as a custom model. So once we do that, then we proceed further and do the initialization step, which will look like this. We do the initialization, which itself, as of now, we are not accepting any parameters. We do the super of custom model comma self dot this. So what it means, what have I exactly done in this line number 3? So in our case, we will need to call the parent class initialization, because we have to manage the trainable parameters of our model. And the trainable parameters are this. So this is the self.w, and we consider this as a trainable parameter, and it is defined as nn.parameter only. And as of now, it is anything random normal, and it will take, and we just want one such value, and the data type is ideally torch dot float 64. Just keep on following what is being shown on the prompt at the top, and you will be getting much idea related to it. And this is how we say that this is something which will be needing a gradient, or I should write it as requires grad. So it will need a gradient to be performed. So the entire purpose of setting required grad is equal to true will mean that we want to perform this gradl by grad w operation on this w. We do the same thing for b as well, and everything else will remain exactly the same, just that we will replace w with b. So we have done the initialization. We know that the parameters w and b are trainable parameters, and we made it much apparent when we set up the requires underscore grad is equal to true over here. Now we are going to specify how the forward step is going to look like. So forward step will take into account 1x, which is mentioned over here, and this is an input parameter, and it has to return torch.exp self.w into x plus self.p. Yeah. So we initialized all these W and B just a step above in lines 4 and 5. And then we say that we are going to return a forward pass. We are going to do a forward pass, which is just taking into account a value of x or a vector x. And then we are going to multiply w with x and add b to it, and then do the exponentiation of it. So this completes our custom model class, and then we are going to call our custom model, which is going to look like this. So we call our custom model. We don't pass any trainable parameters over here. We just initialize two trainable parameters as random normal distribution, and then we mentioned it as double. So this is like the data type which we are associating with it. Now the thing is, whenever we were talking about this loss function, we considered the squared error loss. We can do that over here as well, and we mentioned that our criterion is equal to nn dot msc loss. That's it. And for some reason in many literature the loss is mentioned as criterion over here. Now we will proceed further with deciding our optimizer. So that's also pretty simple. We say torch dot optim dot sgt, and then we say model dot parameters, comma, and there are a lot of parameters, but we are just going to consider the learning rate associated with it. So what we do over here is we say that we are going to apply this optimizer, but only on the model parameters. Now let's take a step back and understand what we have done till now. We initialized a custom model for our task, which will have a suitable forward propagation step, which I mentioned it over here. Now we also have two trainable parameters, W and B, and these trainable parameters needs to be updated with every forward and backward pass of the algorithm. So what we are trying to tell the SGD module is the fact that you have to operate the backward pass only on the model parameters, not on anything else. And for that we have a learning rate as well, which we represented over here by eta. If I scroll down, it will be visible. Yeah, this eta is considered as 0.001, and we are able to initialize the optimizer as well. Now a lot of small and intricate steps will be involved, which will be looking like this. For epochs in range, let's say I prefer to run it for 300 epochs, and the first thing I do is I do a forward pass. So it will work like this. So we forward pass is ideally calling the forward method of this class, and it takes into account the input as the tensor x, which we have defined over here. So as of now we don't know the value of w. It is initialized to any random value, and sim is the value of b. It is initialized to any random value, which is like some random normal value initialized to. We know that it will be upgraded or updated in the future iterations as we apply the optimizer, but as of now the first set of output we are going to get is going to look like this. Now we have done a little bit of prediction over here in this line number 3. We will definitely need to find out the loss associated with it, which is also very simple. We just write it as criterion, and in the criterion we are going to pass the output and the value of y. So this is how the mean squared error loss is calculated. So over here, optimizer dot zero underscore grad will make sure that the gradients of the parameters w and b are set to 0. So in a training step, at each of the successive epochs, when we are doing a forward and backward pass, just to make sure that the gradients are not getting accumulated over different steps, we have to make sure that before doing a backward pass, all the gradients are equated to 0. That's what is done by optimizer dot zero underscore grad. All the gradients will be equated to 0 over here. Once the gradients are equated to 0, we do loss dot backward, and it does the backward pass, and we have to update the weights as well, which is done with optimizer dot step. That's it. In 4 lines of code, we were able to perform one complete forward pass, which is performed over here. So this is the forward pass we did, and this is the loss calculation we did, and we equated the gradients to 0 over here. And once we have equated the gradients to 0, we did the backward propagation step. And in the backward propagation, or we initialize the backward propagation step, and over here we updated the parameters, updated the w and b to make things pretty simple. Now we need to understand how exactly the loss has been propagating over here. Going to print the loss at each epoch, or every 10th epoch, and on doing so, this is what we are getting. You can see how it started with. So we started with a good enough loss over here. Slowly and gradually the loss started to reduce, and by the time it was like about 290 epochs, the loss were pretty much stable. Now we need to see how exactly the weights have changed, and how exactly the loss reduction played an important role in the change of weights. So I modified the code a bit so as to make sure that we are also capturing the values of the model weights at each of the 5 epochs, or after every 5 epochs we are capturing it, and also we are trying to capture the predicted values at each step, or like after every 5 steps we are trying to capture it. So we run the code again, and let's try to see how it works. So definitely we can see the loss is reducing, and it reduced to a certain extent. And then let's try to understand how we are able to visualize it. So I use the plotly express over here, and this is how the graph is actually looking like. So over here, this purple lines denotes the actual values, and the line which is there below, the orange line, will denote the predicted values. Now I play it, and I'm going to play for all the epochs, and will let it stabilize. You can clearly see that for different values, it's trying to fit to the purple line, or the actual and predicted values are trying to get close to each other as and when the number of epochs increases. And from the look of it, it seemed like it is a function which is like y is equal to e raised to twice of x plus 3. Now this is exactly where it reached, and it will stop over here because there were a little bit of random noise in the actual values as well, so getting exact match is a bit tough. So once we followed it, we were able to get the values of w and b in this form. Or if I just play it again, you see from where it started. It started with really some bizarre values of w and b. So it started with minus 0.301 and 1.692, somewhere around there. And then with stochastic gradient descent, it was able to normalize it and reach up to the stability where it needed. So all it needed were few lines of code and not much of the mathematical fuss which we had to do on paper. And this autograd functionality is enabled already in the backend by PyTorch, which made it pretty easy for us to follow. So yeah, so this is how we get the predictions which we needed, and the entire model training took, and this is a shallow network which we created, and the entire model training was done in around 5 lines of code, which involved the entirety of the theoretical concept which we did discuss previously, along with building a custom model for our shallow network. So in future, whenever we are going to build a model, the two things which we need to be very careful of is like understanding what these trainable parameters are, which needs to be put in the model, which I have defined as self.w and self.b over here, because these are the trainable parameters which the optimizer will look for. So once these are defined, the forward step should be defined. As of now, it is just a functional form because we discussed a shallow network over here. In future, whenever we are going to discuss deep neural networks, it will be a bit different. But yes, this forward method should be there in the custom model class which we build in future iteration, along with the fact that it should be calling the base class for all torch function or neural network modules, which is nn.module, which we have initialized over here. So once we are able to do it, this is how we are able to create a basic class for performing a forward propagation. And when we have to do a backward propagation step, this is exactly how we do a backward propagation step as well. All the calculations which we have discussed over here related to computational graphs are all happening in the backend. We don't really need to see it unless we use something like as a tensor board to see it. But as of now, we are not going to discuss that. In the next video, we are going to discuss in detail about one classification algorithm and replicate the exact same steps which we have done over here in the classification algorithm and see how exactly we are able to get correct results out of it. Thanks for your time.